Okay, lesson 27, one sample T procedures. So one sample T procedures is going to refer to the scenario where we have a quantitative variable of interest and we're interested in analyzing the mean. We might be interested in testing it against some claimed value or estimating what that value is. And specifically for T procedures, this is the scenario where we do not know the standard deviation of the population. So we're going to start with confidence intervals, then we'll shift to hypothesis tests. So for a confidence interval, this is going to look extremely similar to last week's. We want to estimate the average value, mu of x of a single population. Our first condition, it's going to be identical. We want to have a sample that is representative of the population. The easiest way to get this is to take a random sample from the population. Based on the central limit theorem, we know that the sample size is big enough that the sampling distribution should be roughly normal. And then here we know or can calculate the sample standard deviation. So here we no longer know sigma of x, but we either know or can calculate this standard deviation from the sample. So here we have the confidence interval. Our point estimate is still going to be x bar because that it will be our best, individual guess for mu. But now we have a t critical, so a t star critical value. Before we had a z star critical value, but now we have t star, and it's because of this change in the third condition. If you know sigma, you can use a z star. If you only know S, you have to use a T star. And then times our standard error. Our standard error here, it's just going to be standard deviation from the sample over root n. It's going to be extremely similar to before, except now I have a T star and now I have an S instead of a sigma. So similar structure, it's going to be a point estimate plus or minus. Everything after the plus or minus is your margin of error. So now we're going to return to this car example, looking at a sports car, probably, hypothetical car. So the car manufacturer, they want to be really, really sure, like what is the average annual mileage for this top-of-the-line sports car? And there's a number of reasons they might want this. In part, it might go into what they anticipate that they'll need as far as coverage, like in warranties go, what kind of wear they might expect on the car. Most cars come with some sort of warranty for a certain number of years. So they go ahead, they take a random sample of 10 drivers, and we get this data set here. So person 1 went 11,501 miles on their car that year. Person 9 went 7,891 miles. So now we're going to break this down step by step. They want to be 95% confident in the estimate. This tells me right away I'm going to be doing a confidence interval. So what is the question of interest? So when we have a confidence interval question or an estimation problem, these questions are going to be open-ended, like what is. So what is the mean annual mileage of all drivers of this car? You could probably get more specific, ask in that given year, in wherever country that they picked. But I'm going to just go down this. So what is the mean? So this is my parameter I'm looking at. And then annual mileage, that's my variable of interest. And then all drivers of this car, that's my population. So what's great is if I set step 1 up correctly, step 2 is going to be a breeze. So what is my parameter of interest? So notation, it's going to be mu. I'm going to put x, because x is going to be annual mileage. And then I'm going to go ahead and put it in words. So remember, this is my notation, is that mu x. What's great is I can pretty much just say, hey, look, mean annual mileage of drivers of this car. That's what goes here. So mean annual mileage of all drivers of this car. Then inventory. So I just want to take stock of what information did I get from the question prompt. So looking here, I have a sample size of 10, which means when we move forward, so degrees of freedom. For T procedures, this is going to be really straightforward. It's just going to be the sample size minus 1, and that's going to be 10 minus 1 is 9. The idea is if I knew X bar and I know 9 of the 10 observations, based on that information alone, I can figure out what the 10th observation is. That's what it comes down to. So then I also can calculate X bar. I'm not going to do it by hand here. You're welcome to go ahead and do that. I threw these into R, had them tell me what it was. So my mean here, 9,467.7 miles, because the annual mileage is in miles. And then my standard deviation for this sample, once again I threw this in R as well, is 2,788.301 miles. So this would be the inventory that I'm looking for. I'm going to need this moving forward. So I know I checked, I skipped over step 3. I promise it's on the next one. Step 4, check conditions. In part, if you check these conditions and you don't meet them, you don't want to keep going. So the first question, we checked these two in lesson 26, but do our data come from a random representative sample? The 10 drivers were a random sample, so yes. Is the sample size large enough that we can count on the central limit theorem to kick in for us? So the sample size is 10. However, they did tell us that the population was normally distributed. So yes, and I'm going to, one thing that we often would do is for this, we would look at a histogram, or we even have a normal QQ plot that we have, and look at it. Like, does this look approximately normal? So it's really hard to tell because there are only 10 observations here. I'd say you might have a low ball. You had that one person that had like 3,000 some odd miles, but everything here, this looks pretty good. And I know it's really hard to tell because there's only 10 observations. On the next slide, we do have a tool that we use to look at it. But let me explain real quick why I'm looking at the sample data. The idea is if I take a representative sample from the population, how the sample data are shaped, I can figure, oh, well, this is probably how the population is shaped as well. It's really, really important that I can assume the data are representative of the population. Because if so, as long as the sample is normal enough, that would be okay to say. And then condition 3, if we know sigma go straight to z methods. We don't, unfortunately, but we do have the standard deviation from the sample, so we're going to use the t methods or the t procedures. So as promised, we have this tool. It's called a normal QQ plot, and the idea is it goes ahead and it fits every single point to this line, and the closer the points are to the line, the more approximately normal the data are. For these 9 data points, it looks very, very good. then you have that oddball. And what it comes down to, it's that one character that only drove 3,000 some odd miles that year. So they're a little bit of an outlier. I would say this does look roughly normal, although it might be worth looking into that low outlier. This is not necessarily something we want you to constantly use, but just know that sometimes it's really hard to just look at a histogram and say, yes, that's normal, or no, that's not. In this case, this was all kind of gravy because we did know the population was normally distributed going in. It's also a little problematic when your sample size is only 10. So step 3. So usually I like to go ahead and check my assumptions before I start doing anything, but absolutely do step 3 first. So the confidence level is 95%. And the degrees of freedom, we said, oh, that's the sample size minus 1, so 10 minus 1, that's 9. So my critical value, so because I meet the conditions for T procedures, I'm going to use a T-star critical value. Last week we were using a Z-star critical value. So I'm going to show you all how we'll find it. So I am going to go ahead, degrees of freedom right here, this tells me which row I need. So I need the 9 row. My confidence level tells me which column I need. So look at the bottom of the table here. I want a 95% confidence interval, so I want 95 here. Where they line up, right here, that is my critical value. So Z-star would have been 1.96. We cannot use that here because we don't know sigma. Instead, we're going to use a T-star of 2.262. And you'll find in general the T-star critical values will always be at least a little bit bigger than the Z-star critical value would have been. And it's because the T distribution is a tiny bit wider than the Z distribution is. Also things to note, looking at this table, it always gives area in that upper tail. So keep that in mind. We'll work at explaining the table a little more when we get to it. Definitely check these out. These are handy for getting used to reading the table. Okay, so putting it all together. I'm going to write this all out again. Let me see. So 9,467.7. I'm going to write miles underneath. 2,788.301 miles. My sample was 10, so my degrees of freedom were 9. The T-star we just got from the other slide was 2.262. So now I have everything I need to plug into here. So my point estimate, so my sample mean, plus or minus, so I'm going to use T-star now, 2.262 times 2788.301 divided by the square root of 10, which is my sample size. Absolutely, feel free to take a pause and test this math out yourself. It's always good to know that you can do it on your own. Because I could always follow along with the teacher, but then sometimes I found out I couldn't always get the same results on my own. So then once I do the plus or minus, remember to put the smaller number first. Just because interval notation, you should have the lower number on the left, you should have the higher number on the right. We're very particular about that one, so just a caution. 7,473.208. My units are miles. We'll also hone in on whether or not you include the units there. And 11,460 2.192 miles. So this is my 95% confidence interval for mu. With 95% confidence, we think that the mean annual mileage for all drivers of this sports car is somewhere between 7,473 miles and 11,462 point some odd miles. Things to note, I tend to not write a comma for the thousands place because it gets really confusing to have multiple commas in there. If you do, that's okay, just make sure that it's readable. That's the key thing. So we'll have one more step after this. We have to write it up into the sentence. So I'm going to go ahead, write this up here. 7 up. I'm going to round to 2 places past the decimal, one place here. Always go out to, I would say 2 is probably the safe place. Definitely if it's in dollars, definitely go out to 2 places. I think in general, WebAssign will want you to go to 4. So fill in the blanks. So the 95% confidence interval, I swear this first blank's the easiest one. Don't forget to tell us the confidence level. We are looking for a mean because the variable of interest we're looking at is quantitative. For the mean what? So annual mileage. Of what population? All drivers of this sports car. Is on average estimated to be between, so those 2 numbers, so 7,473.2 miles and 11,462.2 miles with a point estimate of, so now it's asking, hey, what did you get in the sample? That 9,467.7 miles. And that's just X bar. X bar from the sample. And just to note, like, for the most part, early on, we had you hand calculating means and standard deviations. Unless it's something like 5 observations or fewer, we no longer want you to have to hand calculate those. It's totally okay to throw these into like R and have R calculate it for you. So there's our conclusion. With 95% confidence, for the mean annual mileage of all drivers of this sports car is on average estimated to be between 7,473.2 miles and 11,462.2 miles with a point estimate of 9,467.7 miles. And just note, I didn't drop the units. The units should be included. We will look for them every time, as long as there are units. So now that we've done a confidence interval, we might want to do a hypothesis test. So this is kind of the flip side. So now we want to test the average value, mu, from a population. So we want to maybe say, hey, is the average annual mileage for all drivers of this sports car different than blank? That kind of idea. It's going to be very, very similar to what we were doing last week. These first 2 conditions, they're going to be identical. So we have a representative sample. Typically the way to do this is to take a random sample. And then also we need to know, hey, is the sample size large enough that we could still count on the central limit theorem to kick in? And the condition that's different from last week is that we know or can calculate the sample standard deviation, which is S, or S sub x. So like before, you can have a lower one-sided test where you want to test if the mean is lower than a specific value. The alternative tells you which tail to look in. So less than tells me, oh, well, I'm going to go for the area lower than that. Here, if your alternative is higher than, that means that you're going to look higher. Here, this one's a tiny bit trickier because you have to look at both sides. If you have a negative test statistic, you'll take the area lower, and that's your one-sided p-value. You multiply it by 2 to get both sides. So the test statistic will be a tiny bit different as well here. So before, last week we used a z test statistic. Now we're going to use a t test statistic. The key difference here is it has an s, not a sigma. And once we calculate the t test statistic, we're going to use a t-table, or also r, to get our p-value. We're not going to use a z-table, not for this one. So the test statistic, the reference distribution we're going to use, it will be a t-distribution, specifically a t-distribution with degrees of freedom equal to your sample size minus 1. So we are going to stick with this sports car example. So the car manufacturer in particular now, suppose that they're interested in finding out if the average mileage, annual mileage of their top of the line sports car, are drivers driving differently than 12,000 miles per year. And this, once again, this could factor into a lot of things like what kind of parts that they might expect to need to replace, or maybe what kind of parts they're going to put in the first place. So we're going to assume the population to be normal, thankfully, and we're going to go ahead for performing the test with 0.05 significance level. This should be the same data set, 10 drivers. We get the following data. And these two steps should look very, very similar to what we did with the confidence interval. However, the question of interest is going to be shaped differently with hypothesis tests. Hypothesis tests will have like yes or no style questions. That will be the format of the questions. So specifically, is that average annual mileage different than 12,000 miles? So I tend to say, hey, is the mean annual mileage of all drivers of this car different than 12,000 miles? So that'll be my question here. And that's like at the surface, it looks like a yes or no question. Is the mean annual mileage of all drivers of this car different than this value? What's great is if you set step 1 up correctly, once again, your parameter is just hanging out in the middle of that sentence. The mean annual mileage of all drivers of this car. The parameter hasn't changed from when we were doing the confidence interval. It's the same parameter. So mu of x, and that's just going to be the mean annual mileage of all drivers of this car. Once again, you could probably be more specific. Of all drivers of this top-of-the-line sports car in this given year, but you can probably even get narrower. Inventory, this is going to look really, really similar. There will be a few differences, or at least one. So my sample size is still 10, which means my degrees of freedom are still 9. My sample mean should be the same. So 9,467.7 miles. My standard deviation of the sample should be the same, so 2,788.301 miles. I'm going to throw in alpha. So this is the Greek letter alpha. Looks kind of like a fish. Not sure. Whatever makes you remember it. It's a very confused A. Don't write the letter A. We will jump on that. And then the thing that's going to be different here is I have a claimed value I'm interested in now. So know that mu naught, this claimed value, it is a value that does not come from the sample at all. So the manufacturer wants to know if it's different than 12,000 miles. Okay, well the value came from the manufacturer. So it's 12,000 miles. So be very careful. Mu naught should never come from information from the sample. It should always come from outside. It should come from a claim, or maybe it's a threshold that people are concerned about. That kind of idea. So then my significance level, that's my alpha. It's at 0.05. So now state the null hypothesis and the alternative hypothesis. So things to note is, so mu of x is my parameter. I should always have an equal sign in the null. So the null is 0 default. And we're just establishing the claim. So it wouldn't be interesting if it was exactly 12,000 miles. So 12,000 miles, my claimed null value here. For my alternative, the setup will look very similar. Same parameter, still going to have 12,000 miles here. The thing that's going to change is the sign. And the sign is going to be based on what they say. So the manufacturer wants to know if it's different than. So they don't necessarily want to know, is it higher than it, is it lower than it? They just want to know if it's different. So not equal to. Which means this will be a two-sided test. So when we get down to calculating a p-value, we are going to go ahead and take our one-side p-value, multiply by 2 to get a two-sided p-value. So things to note, you should have the parameter. It should be the parameter, not like we never ever want to see x bar. We will jump on that. You should have an equal sign in the null hypothesis. Then you should have you should have the claimed null value. And don't forget your units. If it's in miles, you should include miles. The main thing that's going to change up here is going to be that sign. So checking conditions. So we did this already, but I'm going to run through them. Do our data come from a random representative sample? Yes. 10 is kind of a small sample, but we did take a random sample of 10. Is the sample size large enough for the central limit theorem to kick in? I mean, it's roughly normal in the sample, but we also were told that the population are normal, so a sample of 10 is big enough. And then, do we know sigma? No. But we do have the standard deviation of the sample. So, okay, so once you've gone ahead and you've checked the conditions, you meet the conditions, we're going to go ahead and calculate our test statistic. So just in order to do that, I'm going to write out the values from our sample, our inventory again. Helps me to have them on the same page. 12,000 miles. It was 88,301 miles. Sample size was 10, so our degrees of freedom were 9. Okay, so last week, when we met the conditions that we had a random sample, that we knew central limit theorem would kick in for the sampling distribution of x bar, and we knew sigma, we went ahead and calculated a z test statistic, because we could use z procedures if we meet those conditions. Because we meet the T procedure conditions, we are going to calculate a t-test statistic, which means our reference distribution is a t-distribution, not the normal. So we're going to go ahead and calculate it by, it's going to be very similarly structured for what we observed in our sample. So the sample mean minus what's claimed. So things to note, what we observed was lower than what's claimed. So when we go ahead and calculate our t-statistic, we should get a negative t-statistic divided by 7,88301 divided by the square root of 10. Go ahead. Obviously, this is not doing your head math. I totally encourage you to go ahead and throw this into a calculator or R. But I get, with some rounding here, about negative 2.87 as my t-test statistic. So just a reminder here, is it one or two-sided? It's going to be a two-sided test because we have a not equal sign in our alternative. So now we're going to go ahead, we're going to pull up a small version of the t-table. You'll notice that I conveniently cut out a lot of what I didn't want out of the table. And get our one-sided p-value, multiply by 2 to get our two-sided p-value. So things to note, our degrees of freedom are 9, and our t-test statistic is that negative 2.87. So degrees of freedom of 9, that tells me which row I want to look in. So this is the row I want. It will take a little bit of practice to get used to using the t-table from the z-table. It does definitely work differently. So now what happens is I'm going to look inside of this row for, and you might notice these are all positive numbers, right? So what I'm going to use is negative 2.87, because remember a t-distribution is centered at 0 and it's perfectly symmetric just like the normal. So if I find the area above positive 2.87, that's the same as the area below negative 2.87. And how I know to go below, so if the null is true, and it is 12,000 miles, the mean is, what we observed was 9,000 some odd, 9,467.7. We are going to move away from the 12,000. So you don't want to go towards the mean, you want to go away from the mean. So I'm going to have this lower tail here. So probability that my t-statistic with 9 degrees of freedom is lower than negative 2.87. That's the same as probability that t9 is above positive 2.87. That's what I was arguing here with this symmetry. So now we're going to try and figure out, well, where does the 2.87 come into this? So this degrees of freedom 9 row, what I'm going to do is I'm going to look for as close to 2.87 as I can get. A lot of the times it might run between two of the numbers. Like it's not between these two. But sometimes it might run off the edge. That's possible too. Obviously, you are free to use R. R will give you more exact if it does that. But here we go. So 2.87 is not there. 2.87, nope, but I'm getting closer. These numbers are getting bigger. No. But here, 2.87 exists somewhere between these two numbers. Right? So what this means, I'm now going to go up and go, hey, look, my one-sided p-value is going to be between those two numbers. Keep careful note of the order they're in. So your one-sided p-value is going to be between 0.05005 is the smaller one and 0.01. It is really easy to write them out of order, to say that it's between 0.01 and 0.005. And that is one of the things we will look for, so be careful. So this is my one-side p-value. My one-side p-value, it's going to be between 0.005 and 0.01. But like I said, I want a two-sided p-value, so I'm going to multiply everything by 2. So all parts of that inequality there. So I'm going to get 0.010, my two-sided p-value, and then 0.02. So my two-sided p-value is going to be somewhere between 0.01 and 0.02. So it's between 1 and 2%. Absolutely, you are free to use R to get a more exact answer. So things to note, my p-value, it's 0.01, so two-sided, 0.02. So my p-value, it's going to be smaller than 0.05, right? So we're not going to intentionally give you a p-value range that has 0.05 in the middle of it. It's really funky. So we are going to reject. Our p-value is small, so we will reject the null hypothesis. I went ahead, I threw it into R. I got 0.0184. Note, this is between 0.01 and 0.02, so I'm happy with what I had from the table. Since our p-value is smaller than our significance level, we're going to reject the null hypothesis with a p-value, and it's okay to write between 0.01 and 0.02 at the 0.05 significance level. So absolutely, you are free to write the range of values in there. So if our p-value is between 0.01 and 0.02, you could say it's strong, it's moderately strong evidence. I'm okay with either one. Evidence to suggest that. And now I have to say the alternative is true, but I have to put it in context of the problem. So I have to talk about sports cars and mileage. So that the mean annual mileage of all drivers of this car is, and here is where you insert the part about the alternative. So the alternative said it was different than at 12,000 miles. So we have strong evidence to suggest that the mean annual mileage of all drivers of this car is different than 12,000 miles. And so what this p-value is getting at, it's saying, hey, if the null were true and the mean annual mileage of all drivers for this car really is 12,000 miles per year, what we observed in our sample, or more extreme, like so further away from 12,000 than the 9,467.7 miles that we saw, that would only happen about 0.0184 of the time if the null were true. Which basically, that's uncommon enough that I think that maybe the null is not true. We think that's unusual. Because there's nothing weird about our sample if it's truly representative. So that is our one sample T procedures. And go ahead, tune in. We'll go into two sample T procedures and match T procedures.